Hello, my name is Sang-Shin. I'm the 6G program lead at Keysight EDA. Today, I will chat with you about 6G technology and how AI research is shaping the AI interface of the future. Let's dive in. The architecture of the 6G network is a comprehensive system that spans various domains encompassing terrestrial, non-terrestrial, and underwater networks. Within this framework, advanced AI interface technologies such as intelligent reflecting surface, ultramassive MIMO, and full duplex communications are seamlessly integrated. These integrations enable dynamic allocations and collaborative use of available frequency spectrum resources, improve the accuracy in determining device locations, and resource management powered by machine learning. These elements represent the central aspect of the network's evolutionary development. It is important to note that a common theme across all these studies is the prominent use of AI. The things we want to measure in 6G networks are much more complicated than in 5G. To deal with these challenges, scientists are using artificial intelligence. They believe that AI can help solve problems that are really hard to solve with regular methods. However, it's important for these scientists to be an expert in both wireless technology and AI because both are needed to make it work well. During this tutorial, I will present three research topics related to 6G, and I will begin with the first one, which is channel estimation. Before we get into the channel estimation, let's explore three main types of machine learning: supervised, unsupervised, and reinforcement learning. These methods each have their own unique features and real-world uses. Understanding them is critical in the world of artificial intelligence. Supervised learning is like having a teacher guide you through the learning process. Imagine you have a data set where each example is labeled. These labels are essentially the correct answer. Your task is to learn a mapping from the input data to these labels. In essence, you're trying to mimic the teacher's knowledge. This is a perfect for tasks like classifying emails as spam or not, or predicting house prices based on various features. Supervised learning excels when you have a clear labeled data and want to make predictions or classifications. Now let's move on to unsupervised learning. Here, you don't have the luxury of a labeled data or teacher to guide you. It's more like discovering hidden patterns or structures within the data. You are given a pile of data, and your mission is to find out if there is anything interesting. One common task is clustering, where you group similar data points together. Think of it as organizing a messy room without labels. Unsupervised learning also includes dimensionality reduction, which helps simplify complex data while retaining its essential characteristics. This is useful in fields like customer segmentations or anomaly detection. Finally, we have reinforcement learning. This is akin to training a dog. Your agent interacts with an environment, takes actions, and receives the feedback in the form of rewards or penalties. The agent's objective is to learn a strategy or policy that maximizes the cumulative reward over time. It's all about making a series of decisions in a dynamic environment. Picture a game playing AI that learns how to win a game through trial and error, like chess or video games. Reinforcement learning is excellent for scenarios where you need to make a sequence of decisions to achieve a long-term goals, such as autonomous driving or optimizing recommendation systems. Now, let's talk about the channel estimation. CNN-based supervised learning can be applied to channel estimation by treating received signal as images, creating a labeled data set, designing a suitable CNN architecture, and training the network. The convolutional layers are responsible for extracting features from the received signal, similar to how CNNs in computer vision extract features from images. The fully connected layers map the learned features to the estimated channel response. In OFDM, non-pilot symbols are inserted into specific subcarriers. At the receiver, these pilot symbols are extracted from the received signal. Channel estimation is performed based on the relationship between the received and transmit pilot symbols. Least squares estimate the channel by dividing received pilot symbols by transmitted pilot symbols. It is simple but less robust to noise and fading. Minimum mean squared error is a more sophisticated method. It estimates the channel using the MMSE estimator, minimizing mean squared error while accounting for noise. Typically offers better accuracy, but with higher computational complexity. The choice depends on system requirements. And this is the process of channel estimation with supervised learning. In this process, we start by collecting data from our communication channel. This data includes the signals we send through the channel and the corresponding channel characteristics. Think of it as gathering evidence about how our channel behaves under different conditions. Before feeding data into our learning model, we perform some data preprocessing tasks. This might include normalizing or encoding the data to make it suitable for training our neural network. Now, this is where the magic happens. We train a supervised learning model like a CNN using our prepared data. The input signal goes on. The known channel characteristics are used as our target or label. The CNN learns to map these input signals to the channel characteristics. Next, we will construct a communication level simulator. To do this, I'm including a 5G base station transmitter on the left, a UE receiver on the right, and integrating the 3GPP channel motor in between, utilizing the Keysight Passwave System Design Simulation software. This simulator serves a dual purpose. It allows me to generate both training data and label data for the training of my CNN-based channel estimation model. Once the model is trained, it replaces the original MMSE channel estimator through the importation of an ONX file. The graph on the right visually represents the performance improvements in terms of the block error rate as a function of a signal-to-noise ratio. CNN-based channel estimation has many advantages. It can learn complex, nonlinear relationship between the received signal and the channel responses, potentially outperforming traditional linear estimation techniques. Despite the numerous advantages, the initial approach of using deep learning for channel estimation encounters several challenges. One such challenge is the disparity in the amplitude of pilot symbols in both time and frequency domains in real-world scenario, leading to variations in the significance of the input features for the neural network. Consequently, preprocessing tasks become necessary before commencing machine learning. Furthermore, there is a risk of overfitting the model to training the data generated under the severe fading channel conditions when employing offline training method. Therefore, it is essential to employ suitable validation technique to ensure the model's ability to generalize. A recent solution that has been explored involves the fine-tuning of an attention-based channel estimator. This approach involves adjusting the attention weight during online training using task-specific data. This adaptive process significantly improves the model's adaptability and effectiveness in extracting valuable insight from data, ultimately resulting in more precise and reliable channel estimation outcomes. To understand this new approach, let me introduce the other concept of the machine learning technique: distributed, federated, and transfer learning. Because the online fine-tuning can be explained as part of the transfer learning, which is reusing the pre-trained models to improve performance on related tasks. Distributed learning refers to the process of training a machine learning model across multiple machines or nodes that are connected in a network. It involves partitioning the data into subnets, with each subnet processed by the different machine. These machines can work in parallel to train the model. Distributed learning is often used for large-scale data sets and computationally intensive tasks, where training on a single machine may be impractical or time-consuming. Examples include distributed deep learning frameworks like TensorFlow and PyTorch for training neural networks on clusters of GPUs or TPUs. Federated learning is a specific form of distributed learning where the training data remains decentralized and is kept on the local devices such as smartphones and edge devices. Instead of sending raw data to a central server, federated learning sends model updates back and forth between the central server and the local devices. This approach allows for collaborative model training without exposing sensitive data, making it ideal for privacy-preserving applications like predictive text input on mobile devices. Federated learning minimizes the need for centralizing data, thus addressing privacy and security concerns. Now, transfer learning is a machine learning technique where knowledge gained from training a model on one task is applied to improve performance on a related but different task. In transfer learning, a pre-trained model is fine-tuned or adapted to a specific task. Transfer learning is commonly used in scenarios where labeled data is expensive to obtain, as it leverages knowledge learned from a broader context. Popular examples include using pre-trained deep neural network like BERT for natural language understanding tasks, or using pre-trained image classification models for specific object detection tasks. In our case, it's an online channel estimation. Now, let's proceed to our second research topic, which is the improvement of channel state information feedback. Massive MIMO is a fancy term for wireless technology that uses a lot of antennas to making things work better. One important part of this technology is something called the channel state information feedback. This means that your devices measure things about how good the signal is, like how strong it is and the way it is moving. Your devices then take this information and send it back to the base station. Because things can change quickly with the signal, these systems always get new feedback and adjust how they work in real time. But there's a problem when you have many antennas and lots of users. It can make a huge amount of feedback. To fix this, we make the feedback shorter and simpler, so it tells what's important without giving too much data. We will discuss how we handle this feedback problem on the next page. The codebook scheme is a standardized approach for beamforming in 5G wireless communication systems. It comprises a predefined codebook that guides the beamforming process. This codebook consists of a set of beamforming vectors, each representing a different beam direction or pattern. By selecting an appropriate codebook vector, a 5G base station can focus its transmitted signal toward a specific user or group of users, optimizing signal quality and spectral efficiency. This scheme allows for dynamic beamforming adjustment to accommodate challenging channel conditions, enabling better communication performance and robustness in 5G networks, particularly in scenarios with multiple users or devices. Compressed sensing is like a smart way to handle data. It's often used in wireless communication, especially for something called CSI feedback. With CS, the amount of data that your device have to send to the base station is much less. This is really helpful when the network has limited space for data or when there are a lot of users. But there's a challenge. You need to find the right balance between sending less data and still making sure it's accurate enough for good communication. This balance is the main thing you have to figure out when using CS. Now, let's explore this idea further by introducing a machine learning technology known as autoencoder. An autoencoder is composed of the three primary components. The input layer, denoted as X. This is where your data is first introduced into the system. Next is the hidden layer, which serves to compress the data, creating a concise representation. Finally, there's the output layer, indicated as X head. This layer aims to recreate the original data from the condensed version. The objective is to train the autoencoder so that the output layer can faithfully replicate the input data, striving for the highest level of accuracy. This concept finds applications in tasks such as data compression, reducing unwanted noise, and extracting key features from the data. In our simulation, we'll be using the same link level simulator that was introduced earlier for channel estimation. This simulator includes components like the base station transmitter, the channel model, and the reference receiver as shown in the diagram. We integrate the autoencoder model into the feedback loop, taking the precoding matrix as input and producing a compressed version as output back to the base station. To generate the precoding matrix at the receiver, we utilize the estimated channel information through a process called singular value decomposition, particularly focusing on the right singular vector. Once this matrix is provided as feedback, it's used to multiply the data symbols before transmission. In these simulations, using the transnet-based machine learning architecture, we observe that the case with compression ratio of 1/4 and 1/8 performs similarly when compared to the scenario with the perfect CSI feedback. The architecture of a neural network plays a significant role in determining the effectiveness of deep learning algorithm and requires meticulous design. Existing design for neural network in the context of a CSI feedback can be categorized into various groups, as illustrated in the diagram. In our study, we investigated two distinct approaches. First, we employed a polar dense network for the implementation of the dual polarization scenario. Second, we explored the application of a novel architecture called the transnet, which heavily draws from the transformer-based design, similar to what is extensively used in models like ChatGPT. Now let's transition to our final research subject, which is the generative channel model. Here's another way to categorize machine learning technique, discriminative and generative learning. Discriminative learning focuses on learning the boundary that separate different classes or categories in a dataset. It aims to directly model the conditional probability distribution P of y given x, where y represents the class label or outcome, and x represents the input feature or data. Common algorithms for discriminative learning include logistic regression, support vector machines. Discriminative models are typically well suited for tasks like classifications and regression, where the goal is to make predictions based on the input data. Generative learning, on the other hand, focuses on the modeling the joint probability distributions of both the input data and the class labels. Common algorithms for generative learning include the Gaussian discriminant analysis and generative adversarial network. Generative models are useful for tasks like data generation, denoising, and anomaly detection, as they provide a more comprehensive view of the data distribution. So, we will use the GAN for our channel generation research project. GANs consist of a pair of neural networks, namely a generator and discriminator. The generator network takes random noise as input and strives to produce data that closely resembles real data sourced from a particular data set. It learns to grab the synthetic data samples that are highly similar to the actual data distribution. The discriminator network operates like a binary classifier, distinguishing between genuine data samples from the dataset and counterfeit data created by the generator. As the training process advances, the generator becomes more proficient at generating lifelike data, while the discriminator becomes increasingly adept at differentiation. Ideally, this back and forth continues until the generator created data that is virtually indistinguishable from real data. GANs find a widespread application in various tasks, including image generation, style transfer, and data augmentations, and more, where the goal is to create fresh data samples that closely resemble genuine data. This is an updated version of the GAN diagram devised for learning the channel generation process. The structure depicted in the illustration comprises two distinct subnetworks, the generator G and the discriminator D. The generator's objective is to create a counterfeit channel, denoted as G of Z given C, conditioned on the distance information C. Meanwhile, the discriminator acts as a classifier, working to differentiate between genuine channels, represented as H, and synthetic channel, denoted as H hat. These two networks are subsequently trained through an adversarial process, akin to a competitive game with zero-sum outcomes, where each network's gain is the other's loss. Moving to the next page, let me address some important point about the real channel H. In general, preparing real channel data to train GAN model is not trivial. High-dimensional wireless channel and spatial temporal channel are two different aspects of wireless communication channels, and they have distinct characteristics. High-dimensional channel refers to the channel with many correlated paths. Typically, they are associated with multiple antennas at both transmitter and receiver, leading to spatial diversity and can increase capacity and spectral efficiency. However, sometimes it is inefficient using this high-dimensional channel, but it is sparse when sparse, such as millimeter wave and subterraneous channel. The huge size of a channel matrix may contain only few meaningful information. In this case, spatial temporal channel can be utilized with a reduced number of the learned parameters. It captures the dynamic nature of the wireless channel, where the channel conditions change over time due to user mobility and environmental factors. However, dealing with spatial temporal channel often requires more sophisticated signal processing and adaptation mechanism to maintain link quality. Now, let's look at our simulation case study. First, we use the 3GPP channel model to generate the real channel data. The third generation partnership project has developed standardized channel models that are widely accepted in the telecommunications industry. These models are used for the performance simulations, system design, and standard compliance testing. Game-based models are created using machine learning technique, specifically generative adversarial networks. They are a departure from traditional analytical models. They can generate synthetic channel data based on the training dataset, enabling customizations for specific scenarios or environment. They are trained on real channel data, in this case, 3GPP model, allowing them to learn and reproduce complex channel characteristics and variations. Game-based channel models are relatively recent developments, and their adoption is increasing in research and development for wireless communication and beyond. I'd like to introduce a new way of creating more realistic wireless channels. Stochastic channel data represent the randomness in wireless channel. Deterministic channel data represents specific scenarios or characteristics you want to simulate, like line of sight or non-line of sight conditions. Measured data is information we get from real-world measurement of the channel in specific locations. To make the GAN create channel data that combines both randomness and specific features from measurement, we can use domain adaptation techniques. These techniques help the GAN understand and generate all types of the channel data. We can use methods like domain adversarial training or conditional GAN with special settings for specific features. AI and ML serves as a fundamental technologies underpinning various facets of 6G. The machine learning process can be summarized in 3 straightforward stages: data generation, model training, and deployment. In each of these stages, the use of the AI-driven simulation platform is essential for advancing your research on air interfaces. Thanks for watching.